we are going to talk about finding the area between two curves. Using definite integrals. We are going to talk about three things. The first one being y, and the second one is the derivation, and two examples if time permit. So to answer the question why do we need to use definite integrals to calculate area between two curves, is because this allows us to find areas that are of irregular shape, and also allows us to put in boundaries of the area of interest. Now, having questioned the why, let us jump into the derivation. For the derivation, we are going to focus with respect to x-axis for the moment. It is possible to derive the same equations for areas with respect to y-axis, but for this example, we'll work only with the x-axis. Let us consider this diagram where this is the x-axis, this is the y-axis, and we have two graphs f of x and g of x. F of x is the graph on the top, g of x is the graph in the bottom. And we are going to write the condition as f of x and g of x are continuous functions. Now, we said we are going to use definite integrals, so we need to produce some limits. So let us say we want to find the area between the ranges A, B, or in other words, this dotted region is our region of interest. We want to find this particular area. So we can add to our description of the problem as f of x and g of x are continuous functions over the interval a, b, such that f of x is greater than or equal to g of x on AB. Okay. Now, in order to find out the area, we apply a very simple trick. The trick is to put in very thin rectangular strips that can fill up this region of interest. Let me draw one of those thin strips. Now, the way we have drawn this strip, we need to add another additional piece of information. This dashed black line passes through the middle of this thin strip and intersects the upper and lower function at 2 points, such that the point of intersection of this dashed line on the upper function is called f x star I, and the bottom point is labeled as g x star I. Now, additionally, the width of this rectangular strip is delta x. What is the purpose of this? You will observe that now we can easily find the area of this thin rectangular strip. How? Delta x times the difference between fxi star and gxi star. Or in other words, we are going to make this thin rectangular strip thin enough as if it were representing just this line. Okay. Now, the height of this rectangular strip can be written as f of x star I minus g of x star I. The width of the rectangular strip is equal to delta x. So the area of the rectangular strip is given by the height of the rectangular strip times the width, or f of x star I minus g of x star I times delta x. Now, to find out the area under the curve, we have to add many such thin rectangular strips, which can then be written as A equals, is similar to summation of I equal to 1 to n, I being just the position of this thin central line at one location. As I move this rectangular strip along in between these two graphs along the x-axis, the height is going to change and therefore capturing the area of that next little segment. So the total area would be the summation of all those little tiny areas of the thin strips, given by this expression now. As n tends to infinity, that is, we consider infinite number of thin strips, we can write this as area equals, now this is an equal sign, limit of n tends to infinity. So essentially this equation is the difference equation, and then we are essentially taking that difference equation and converting it into a calculus notation. Which is equal to which is the general equation for finding the area between two graphs along with respect to the x-axis. Now, let's look at an example. Let's look at an example. Let us consider this following graph. This is the x-axis, this is the y-axis. We have a parabola like so, and a straight line like so. And we are interested in the area given by this dotted sign. So let us write the problem. The problem is, if R is the region bounded above by the graph of a function f of x equals 9 minus x over 2 whole square. Obviously this is the equation of the parabola, so this is 9 minus x over 2 whole square equal to f of x, because note, for the given area of interest, which is this region R, the upper graph is the parabola. And below, by g of x equal to 6 minus x, which is obviously the straight lines equation, our job is to find R. To solve this problem, first we have to determine the region of intersection. So this is a very important point that we have to find out. We observe that the straight line and the parabola intersects at a point in two locations. So first we have to find out the points of intersection. So our first goal is to find points of intersection. This is done by making f of x equals g of x. If I make these two equations the same, then we can find out the points of intersection. To do that, we write then 9 minus x by 2 whole square equals 6 minus x, and then we go on to solve this to find out 9 minus x squared by 4 equals 6 minus x. This gives us x squared minus 4x minus 12 equals 0, or x minus 6 x plus 2 equal to 0. Therefore, the points of intersection happen at x equal to 6 and x equal to 2, x equal to minus 2. So then on the positive side, that point is x equal to 6, and that location is x equal to minus 2. Now, interestingly enough, this is what gives us the upper and lower limits for the definite integral. Now, to find out the area, we use the same equation that we have discussed before, a to b f of x minus g of x dx, which is equal to minus 2 to 6. F of x is 9 minus x over 2 whole squared minus 6 minus x. dx, which is equal to minus 2 over 6, 3 minus x square over 4 plus x dx, which is equal to 3x minus x cubed by 12 plus x square by 12 over the region minus 2 through 6. And if you simplify this and apply the difference equation, we get the solution 64 by 3 units squared. This is how we can find the area between two curves over any given limits, and this is how we can easily calculate the areas of irregular regions using definite integrals.